तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will look at solving linear programming problems. We will start by considering a simple example and then see first the graphical method to solve linear programming problems. The problem that we will take up is to maximize (6x1 plus 5x2) subject to x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, x1 x2 greater than or equal to 0. You may recall that this is the problem that we formulated in our first example. We will first see the graphical method to solve this. So, I am sure you would have learned how to draw graphs corresponding to inequalities earlier. We will do that. Now, let us first try to represent both these constraints in the form of a graph. We call this x1 and x2. We are only looking at the first quadrant because we have both x1 and x2 greater than or equal to 0. So, we will not look at the remaining 3 quadrants. So, we first try to represent x1 plus x2 less than or equal to 5 in the form of a graph. So, we first draw x1 plus x2 equal to 5. So, we try to identify 2 points that are on the line x1 plus x2 equal to 5. So, the 2 easy points would be 5 comma 0 and 0 comma 5. So, we draw the line, this is x1 plus x2 equal to 5. Now, this line divides the quadrant into 2 regions, one which will be less than or equal to 5 and the other greater than or equal to 5. The origin 0 comma 0 being less than 5 would mean that this is the area which is x1 plus x2 less than or equal to 5. So, we just mark the region x1 plus x2 less than or equal to 5. Now, we try to plot the other one 3x1 plus 2x2 less than or equal to 12. So, we first plot 3x1 plus 2x2 equal to 12. So, 2 corner points that we can think of are 4 comma 0 here, this is 5 comma 0, this is 0 comma 5. The other one is 0 comma 6 which lies on the line 3x1 plus 2x2 equal to 12. So, we draw the line joining. So, this is the line 3x1 plus 2x2 equal to 12, this is x1 plus x2 equal to 5. Again this line divides the first quadrant into 2 regions, one which is less than or equal to and the other greater than or equal to. So, once again we evaluate 3x1 plus 2x2 at 0 comma 0 and realize that this is the portion that is to the left of it is less than or equal to 12. So, this is the region which is 3x1 plus 2x2 less than or equal to 12. You can see this on the graph sheet as well here. You find that the first one is between 5 0 and 0 5, the other one is between 4 0 and 0 6 which is shown here. The shaded region shown in this figure is actually the region that is common to both these constraints, this constraint as well as the other, and that alone is shown here in the shaded form. So, in this graph you will see that this represents the region which is common to these two. So, this two constraints are now represented by this region which is shown in this graph, and this is the point of intersection which is 2, 3. Now, let us look at this region. Now, every point inside this region satisfies both these constraints. Now, for example, if we take a point say 1, 1 which is inside this region. Now, 1, 1 satisfies both these. Now, 1, 1 has an objective function value of 6 plus 5 11. Now, we are interested in trying to maximize the value of the objective function. So, what we can easily do is, if we are considering a point 1, 1 here, you could always move either in the right or in the upward direction or left or downward direction and start moving and trying to see if there are better points than the point that we have chosen. So, if we take 1, 1, because both these coefficients are positive, it is possible either to move in the right hand side direction or in the upward direction to get points which are better than 1, 1 with respect to the objective function 6x1 plus 5x2. Every point inside this region satisfies all this. We also know that every point outside this region violates at least one constraint. For example, a point here would satisfy x1 plus x2 less than or equal to 5, but would violate 3x1 plus 2x2 less than or equal to 12. So, our region of concern and interest is only this shaded region. So, if we now try to get better points by moving either to the right or to the or above, then we realize that the farthest we can go is actually up to the boundary of this region. Or to put it simply, for any linear programming problem, for every point that is inside this region, there is always a point on the boundary which will dominate that point with respect to the objective function. If there is a negative coefficient, then you would move either to the left or below depending on whether it is for x1 or x2. If there is a positive coefficient, then it is always advantageous to move to the right or move to the top to find a point which is on the boundary. Therefore, we can now say that even though every point in this region satisfies these two constraints, because we have an objective function which is linear, you will have a situation where we are interested only in the boundary points, because for every point inside this region there is always a point on the boundary which will be better with respect to the objective function, even though all these satisfy the constraints. So, our focus immediately shifts now